All right, so oops. So the talk that I'm going to give today is on the cultural brain hypothesis, which is a theory for the evolution of brains in general, as well as the related cumulative cultural brain hypothesis for the evolution of human brains. How that relates to an idea that we call the collective brain or the collective brain hypothesis, and a little bit toward the end on the evolution of intelligence. And in the background here, you'll see Michelangelo's creation of Adam, which often comes up with talks on brain evolution because, of course, God is in this kind of brain-like veil, I suppose. But what this talk is really about is that kind of broader picture. So some people forget that the creation of Adam sits on the Sistine Chapel's ceiling and is surrounded by various other related paintings. And that's really what this talk is about. So it's about all of these features that we find across species that seem to be connected to one another and that can help us understand the evolution of large brains and the human brain. Okay, so what is the research puzzle? The first part is that the hominin brain tripled in size in the last few million years, and it's roughly 3 times as large as a chimp brain. And the human brain wasn't alone. The hominin brain wasn't alone. The brain size in other taxa also increased. And you might think, yeah, that's amazing. Bigger brains, more storage, more management of information, more thinking. Why don't we all have bigger brains? And that is the puzzle. If it really were the case that this was universally good, then you would expect enormous brains across the animal kingdom. But there are, of course, costs to this, one of which is that brain tissue is energetically expensive. And that is, you should really want the largest brain that can pay for itself in the sense of evading predators and finding calories to pay those energy costs. You want to get away with the smallest brain that lets you do all those things. Now, alongside that, rapid increase in the human brain has also been, and beyond the rapid increase in the human brain, has been a rise in cumulative culture. So a rapid rise in cooperation and cumulative culture. And more recently, when we've been measuring it, a rise in IQ test performance, the so-called Flynn effect. And I guess what I'd like to do is to try to connect all these pieces together. So in case you want to leave early, I'm going to kind of throw the take-homes right away. So the first is that the cultural brain hypothesis and the cumulative cultural brain hypothesis, I think, can help make sense of correlated features that we see across the animal kingdom, as well as some of the specific features that we see in humans. And so I kind of go a bit beyond the model to kind of show you how those pieces, I think, fit together. The second is that the collective brain hypothesis follows naturally from the cultural brain hypothesis and can help us understand and explain the rise in cumulative culture. And finally, that rise in cumulative culture can help explain the rise in IQ test performance. Okay, so I'll be drawing on. Let me put it this way. So I won't be going into the details. This is very much kind of a public talk. But if you want those details, I'm primarily drawing on 4 of my papers. The first is a paper on the cultural brain hypothesis that presents an analytical model and a computational model, as well as several tests of the predictions with primates. The second paper is a second test of the cultural brain hypothesis, this time with cetaceans, so whales and dolphins. So, chimps and other primates are quite different to us, but at the end of the day, they're primates. They live on the land and so on. Whereas whales and dolphins are quite alien. They live in this strange underwater world. So if it is true that there are these kind of broad patterns that govern brain evolution and correlated features, then we might expect, or we might be able to test these in very unrelated taxa. And we were able to do that with a new data set of whale and dolphin data that we put together. The third paper is a paper on innovation in the collective brain, which lays out the collective brain and specifically talks about how it relates to innovation. That paper briefly touches on the relationship between the collective brain and the evolution of intelligence, but we talk about it a little bit more detail, contrasting it to behavioral genetics in a new working paper that's currently under review on cultural evolution of genetic heritability with my student Ritaro Ichiyama and my postdoc Rachel Spicer. Okay. So that's a bit of background. All right, so let's deal with the cultural brain hypothesis first. So just for some quick background, brain sizes got bigger. They tripled in size in the last few million years. And as I said, hominins weren't alone. So this is various mammalian taxa, primates, cetaceans, and so on. You can see the encephalization slope, that is how much of an increase took place, varies. Primates had the largest, followed by cetaceans. But you can see this kind of increase across the animal kingdom, and that needs explaining because brain tissue is energetically expensive. And there are many explanations that have been proposed. And these explanations can kind of be clustered into four broad categories. So there's explanations to do with the climate, that there were certain climatic changes that resulted in, more challenges or maybe greater calories that resulted in these brain and body changes. Relatedly, ecological explanations. So either the ecology is challenging and requires a larger brain, or the ecology is plentiful and can support a larger brain. There are also explanations that center around a technical intelligence hypothesis. This is particularly popular in explaining cephalopod intelligence, so octopuses. And, this is, for example, to do with the fact that we have hands and they have tentacles and they can manipulate their environments, as one example. I think the most popular of these explanations is probably the social explanations, and the social brain hypothesis, Machiavellian intelligence hypothesis, and related hypotheses are probably the most popular. Robin Dunbar is famous for his correlation shown between the neocortex ratio and the mean group size among monkeys and apes. And so for that reason, I kind of want to contrast the cultural brain hypothesis to the social brain hypothesis. And the way I think about it, and the way I think it really applies, is that the cultural brain hypothesis is not so much a contrast to the social brain hypothesis as it is kind of a formal generalization of those ecological and social hypotheses. It kind of draws everything together and explains how these patterns might be related to each other. So actually, in that whale and dolphin paper, I wrote it with Suzanne Schultz, who worked with Robin Dunbar on the social brain hypothesis, and I think we're both satisfied that it tests both of these. So what is the difference for those more familiar with the social brain hypothesis? The first is that famous relationship between brain size and group size in the cultural brain hypothesis is an indirect relationship, as you'll see in a second, not a direct relationship. So it's not that, brains are adapting to social group living, it's that they are adapting to information, and information under particular circumstances is structured in a social group for social learners. The second and the most important shift, I think, is that we move the emphasis from brains for life in social groups, what I sometimes call tricking and tracking. So, tricking other individuals or tracking them. Beyond the complexities of life in social groups, brains are certainly for that, but they're also more generally for learning. They're for storing and managing and applying information, just as you think they are. And so really, as I said, the cultural brain hypothesis can be thought of as this generalization of these other hypotheses. Okay. So what is the cultural brain hypothesis? Here it is in a nutshell. So the idea is that brains are for storing and managing information. They constrain how much information or how you can deal with how much information you can store, manage, use, and so on, right? And we find a correlation between, for example, absolute brain size and some form of intelligence or cognition across the animal kingdom. There are constraints on how you can acquire that information. So one way of acquiring that information is through your life experience, trial and error, experimentation, what we might call asocial learning. And another way to acquire that information is through learning from other members of your group, so social learning, right? But both of them can lead to more information, and more information, more adaptive information, increases the carrying capacity or increases the number of surviving individuals, can create larger groups. And so even among asocial learners, we might find some mild relationship indirectly between brain size and group size because of this relationship between these three components. However, if you are a social learner, then group size does something else for you. And that is that larger groups, higher sociality, so larger, more interconnected groups, offer more opportunities for learning. It offers more information to learn, right? And as the information begins to build up, if you, for example, become unconstrained by what you can learn over your own lifespan because you are learning from other individuals, so you can see I'm kind of hinting toward the human pathway, then you can create a selection pressure, or at least strengthen the selection pressure for larger brains to manage this ever-growing amount of information, right? And so you can kind of move into this kind of autocatalytic takeoff. You can take this kind of this feedback loop between all these pieces. which can in turn enhance or strengthen your tendency to rely on that very now useful social information, which is more accurate than figuring things out on your own, especially if figuring things out on your own is costly in some way, either because it's inaccurate or it's just difficult and costly to do. But you have to deal with this ever-growing amount of information. And so you can deal with it in other ways. We're going to go over many of these because they relate to the collective brain. One of the ways that you can do it is to just spend longer learning. So you can extend your juvenile period either genetically by just extending childhood or even culturally as kind of cultural adolescence. So you can delay the moment from when you can reproduce to when you actually do. All right. Which in turn, offers more opportunities for social learning and, according to the model, also strengthens your ability to engage in that social learning. So more reliance on oblique learning, so learning who else I might learn from, and more emphasis on learning strategies. So, for example, we find a correlation between females in a group. So chimps learn from their mothers, and in part, that's because that's who they spend time with. But you can imagine if you have access to more than just mom, you have Aunt May and Aunt Martha, and you're trying to decide between them, you can begin to develop these learning strategies for who actually has more knowledge. And as I'll argue in a moment, cooperative breeding might have been helpful in making that transition. So the cultural brain hypothesis is made up of this analytic model as well as the simulation. And from that simulation, you can derive some relative correlations between these various features that we look at: brains, adaptive knowledge, group size, social learning, and the length of the juvenile period. And you could look across all of these in general, but in the model, what we actually find is that there's two strategies that animals can take. If you start with a world without any social learning, the dominant strategy is asocial learning. You can still get to social learning. It seems like a powerful strategy, but you don't get it quite as much as you do asocial learning. If you start the world with some amount of social learning, you enhance the social learning as a strategy. But there are very much two regimes in the model, and so what we can do is we can derive two sets of predictions for the social learning animals and predictions for the more asocial learning animals. Now, as you and I all know, there are many biases in science, and one of those biases is towards studying things that are novel and interesting. So you don't publish in Science and Nature by showing that adults are kind of stupid and babies. You don't show that adults are smart. Human adults are smart, and babies are stupid, and animals also kind of stupid. You publish those Science and Nature papers by showing that actually, look at this clever animal. Look at what it's capable of doing. Can you imagine that babies are capable of this? Also, adult humans constantly making mistakes. So that bias also goes into the kind of animals we look at. We tend to look at animals that show this kind of interesting behavior, particularly more social learning animals, particularly those like ourselves. And so we know a lot more about social learning animals in terms of these things than asocial learning animals. These are some of the correlations that we're able to test because we know that they exist in the world, and that's what we tested in the original paper. So relationship, for example, between brain size and group size, famously. So I'm gonna kind of point to a few of these tests drawing on the paper. One, for example, is the data from our simulation. So the simulation is creating all these kind of equilibrium level species, and we find that group size is well correlated with brain size and group size are well correlated, more so if you're a social learning animal than if you're an asocial learning animal, which is actually, strangely enough, quite similar in the correlation to what we find in the Dunbar data. This is a subset of the test, but I'll do three. Here's another one between brain size and reliance on social learning, at least among primates. Obviously, you find this relationship among social learners, not so in asocial learners, which is the same kind of relationship you see among primates. In some of the work with Kevin Leyland and his colleagues. And you can also look at, this one I find interesting, so I kind of pointed it out, is that we find a relationship, or we predict a relationship between brain size and the juvenile period. We find a stronger relationship. This is still fairly weak relative to some of these other relationships, but we find a positive relationship among social learners. And we find a negative or non-existent relationship with brain size and juvenile period among asocial learners. Now, the way that the juvenile period is modeled in the cultural brain hypothesis is not, put it this way, I would do it differently were I had to do it again. Nonetheless, I think there is a useful insight here, and that is that if you're a social learner it pays to extend the juvenile period because you've got so much to learn, and there's more stuff you can pay attention to, and there's more time that you can spend learning. So think about in our society how the world has become more complex, and how it used to be that high school, it used to be that just an internship or an apprenticeship was enough. Then it was kind of high school was enough. Then it was kind of an undergraduate degree. Then it was an undergraduate degree and a master's, and then a master's plus an unpaid internship, and so on and so forth. Right? As the world becomes more complicated, you just spend longer learning as one strategy. I'm foreshadowing some of the collective brain stuff. But if you're an asocial learner, you're doing things on your own. And so the efficiency of that learning is far less than it is for the social learner. The social learner is like the kid in class who cheats. You don't have to work it out on your own. You just turn up and copy what other people are doing. Asocial learner has to do it on their own. And so you want to get that learning period over and done with as quickly as possible. So you move on to the, I really like Alison Gopnik's kind of explore exploit way of talking about this. So you got to move very quickly from explore over to exploit. And of course, we do find this relationship between brain size, neocortex, and relative juvenile period among primates. So, as I said, primates are still fairly similar to us in many respects. So we wanted to test this on a very alien taxa. And so we looked at whales and dolphins, where there is a lot of data out there in the world. It's just scattered. So my colleagues, Kieran Fox and Suzanne Schultz, and I put together this large data set. And then we ran a path analysis to see what are the best fitting relationships. And consistent with the cultural brain hypothesis, what we find is that brain size is strongly connected to social repertoire, and is actually connected to not the largest groups, but the groups where there's the most amount of social interaction. So you get these kind of big, schools almost of whales in particular, but then the toothed whales and the dolphins in particular have these more tight-knit social groups, and that's where you get the large social repertoires and large brains. Okay, so we've been able to test to some degree with the data that is available many of the relationships among social learning taxa, but we have an entire set of predictions for asocial learning taxas. So that's the next step for us. We have a new grant from the Templeton World Charity Foundation, and we're doing exactly the same method that we did for the cetacean paper for cephalopods. Cephalopods happen to also be an intelligent species, and so there is actually data out there in the world, and we're putting it together into a large data set and basically conducting exactly that strategy to test these relationships as a starting point, and hopefully build a better theory if we can't make it work. All right, so if we return to the cultural brain hypothesis, within the cultural brain hypothesis model, there is a set of parameters that lead to this kind of massive takeoff in brain size, group size, the amount of adaptive knowledge, the reliance on social learning, the juvenile period, the tendency to use oblique learning and to enhance your learning strategies, right? And so we want to know what conditions lead to that takeoff. And we find 4 parameters in our model. The first is transmission fidelity. That is, you need to actually be copying without really understanding. You should be trying to copy as much as you can. So one of the big differences, we see in experimental data between the way that chimps learn and the way that humans learn is that it's not that chimps don't have the ability. There's debate around this, but I do think the chimps seem to have the ability to copy and to pay attention and copy, as in the famous Victorian Horner and Whiten experiments with the magical fruit. But they certainly don't seem to have the proclivity to do that, whereas humans do. We tend to copy and do things without understanding them, and we do it all the time. We hold in our heads many beliefs that we actually have no real way to verify. You will swear up and down that you live on a spheroid rotating around a star, one of many stars in the Milky Way, one of many galaxies in the universe. You believe that with all your heart, even though it violates your own everyday experience of a flat Earth and a sun tracing the sky from east to west. It's not that the evidence doesn't exist. I'm just not convinced that you have access to it, nor am I trying to convince you that the Earth is flat. But the point is that you learn so much of these recipes. Like, your computer may as well be magic. You don't know how your Wi-Fi works. You just know that you press a sequence of buttons. When you cook, you don't have to understand the way chemistry and biology work. You just know that you can follow a recipe and have something edible. Now, if you want to argue for this kind of autocatalytic takeoff for humans, it needs to be fairly early. And so I think this goes beyond the model, but I think that there were probably some pre-adaptations that set the stage for this kind of takeoff. One of those pre-adaptations may have been, for example, bipedalism. Mainly because, so this is maybe around 400 million years ago, about 4 million years ago. Bipedalism frees up your hands, which does a couple of things. One is that it allows you to gesture, right? So you can supplement your guttural utterances with kind of gestures and have this kind of Baldwinian style process where you can learn particular gestures as being associated with certain things. And if there's enough knowledge, there's enough to try to transmit, then the system that you're using, the proto language, can genes that can help you do that better are selected for. And so you can kind of get this takeoff where language starts to become better and better. The second thing that bipedalism would do is that it can cheapen the cost of, I should say, so the other thing is, consistent with the cultural brain hypothesis, you can also have kind of early strategies that enable you to increase your transmission fidelity. So things like gaze following and shared intentionality and theory of mind, which have been implicated, I think maybe these kind of proto-genetic changes, which then get supplemented all the way to radio, television, and the internet today. All ways of transmitting the information more effectively. The second thing that bipedalism might have done was that it cheapens the cost of tools. So if I'm a quadrupedal ape, I make something, and now I got to carry it. It's pretty hard to carry, so I'm going to have to make it somewhere else. But if I invest time in building these kinds of tools, then if I can carry that around, I've cheapened its cost. So it's more worthwhile putting more effort and time into building stone tools. Now we have evidence for stone tools. What we don't have is, this is an absence of evidence, but we don't have evidence for what might have come before, sharpened sticks of the kind that we see, or stick tools as we see in chimps, but, sharpened sticks and maybe tools made out of bone or tools made out of wood. Okay. One bit of evidence, I think, for this kind of early culture is that we've had control of fire for a long time, let's say 1 to 2 million years. So there was something that was worth learning that might have kind of set this process described in the cultural brain hypothesis and the cumulative cultural brain hypothesis off. The second feature that we find in the cultural brain hypothesis that might have helped in the rapid rise in the human brain is we find the reproductive skew, or we predict the reproductive skew should be fairly low. So kind of monogamish behavior, not to the point where everything is genetic, where if you are a genetic winner, you win huge. There needs to be some amount of variation in the population. Cooperative breeding might be one mechanism that allows for it. I quite like the idea of cooperative breeding as a mechanism that would have done this, because it would have solved that problem of learning from mom and kind of created this gradation to start to look at, it's not just mom, but the many moms and the many dads that I have access to. And now it's not a matter of access to information, it's a matter of who actually has better knowledge. So you can kick off the learning strategies and the oblique learning in this way. The third feature that we find is smart ancestors. So if you've got some amount of knowledge that was acquired asocially, as many other models show, then social learning can exploit that amount, can exploit that asocially learned knowledge. So I really like, in the original kind of Boyd and Richardson predictions, this idea that you've got this rapidly changing cultural variation, followed by this kind of more moderate. That rapidly changing is the exact zone where you would expect to see more asocial learning, which could then be exploited by the social learners. And it's probably linked to something like generation length. And the fourth is that there needs to be a rich enough ecology that you can begin to unlock resources to pay for those hungry brains, right? So this gets tricky. So some people would say, well, if the ecology is challenging, this selects for more intelligence. And I think, there's some truth to that. But also it needs to be, at least potentially, there needs to be enough energy. There needs to be enough calories in that environment, more like a forest than a desert, so that at the very least, if I had the information, I could, in principle, unlock the calories to pay for that brain. Okay. So we can move from the cumulative cultural brain hypothesis and the cultural brain hypothesis to collective brains. So what happens when you've got these brains that are in a society that has enough information spread across, that we're learning from multiple people? It has lots of information to learn, more than I can learn in my lifespan. And I've got a brain that is engaging in learning strategies, oblique learning, trying to figure out who's got the knowledge, who should I be paying attention to? What happens? What kind of structures lead to more rapid cumulative culture? And that's what the collective brain tries to deal with. So let's move on to kind of innovation in the collective brain. Ooh, I'm going a bit slower than I expected to. All right. So knowledge starts to grow. brains are trying to keep up with that knowledge, and eventually you max out on brain size. One nice bit of evidence, I think, for this maxing out on brain size comes from the medical literature. So this is Lipschutz et al. 2015 in the American Journal of Obstetrics and Gynecology. What we have on the x-axis is its head circumference. So doctors used to think that big babies were hard to birth, or it was totally random. It turns out it's not big babies, it's big heads that are difficult to birth. On the y-axis, what you have are unplanned cesareans and unplanned instrumental births, right? So these are not planned. These are things that we had to use them because we had no choice. And you can really see that even in the small amount of variation we see in human head sizes, once you get to about the 85th percentile, the thing just hockey sticks up, right? So that it still might be useful to have a bigger brain if you can birth it. It might be worthwhile. Okay. How else can we do this? As I said, you can extend your juvenile period, move from kind of a genetic juvenile period to a cultural juvenile period, which creates new selection pressures. So not so much the ability to birth a big brain, but just the ability to give birth at an older age, to be fertile older. You can begin to increase your social learning strategies. So in a small scale society, in a hunter-gatherer society, there might not be a lot of teaching going on explicitly. It's more like slow down and allow kids to hang around. Once you've got more to learn, or the package is larger, suddenly you have to slow it down. You need to do deliberate instruction. If we zoom all the way to the Industrial Revolution, suddenly we've got to prepare workers for this brand new, more difficult environment. And so we have schools where we try to efficiently download a cultural package onto our kids as quickly and efficiently as possible. Phonemes, numbers, let's go, let's go, let's go. And we've been constantly trying to improve that cultural transmission through educational interventions and through technologies that help. And of course, this in turn shapes our society in many rich and profound ways, right? The first is that it creates the need for either cooperative breeding. One could argue that even in our current society, we engage in a kind of cooperative breeding in the sense that we provide benefits to single mothers and to parents and so on. We're helping to supplement childcare, right? But it also creates all kinds of problems for society to solve. You're now giving birth to these floppy, useless messes of babies, these premature babies, effectively, not ready like the gazelle to run off, not even ready to kind of latch properly. And so you need some help. So you need the allo parents, you need the society, or at least you need dad. And dad, of course, needs to know it's his. And different societies have solved this in different ways, from, the unusual, from the very common, control female sexuality and control male resources, to the more, rare situation where you don't have dads. Brothers are just supposed to look after their sisters' children. There's some nice work in economics on this, Alessina Giuliano and Nunn and Anke Becker's work, where they look at, for example, the way in agriculture, pastoralism affects the amount of control over female sexuality or the division of labor. The other thing that this can do is that it might not only kind of push on the length of the lifespan, but also create grandparents. Grandparents, as per the kind of calorie grandmother hypothesis, Kristen Hawk's version, which would be grandparents helping with resources for the young children, but also kind of information grandmother hypothesis. Parents are young; they're incapable, or they don't have as much knowledge as a grandparent who managed to survive for a long time. And so grandparents serve as a kind of Wikipedia of their time. They can broadcast to many children, so they're looking after those children, but they're also giving them a lot of information. And it's quite possible that's the reason we have things like menopause. And of course, our groups grew, both in size, the population size has increased, but also in terms of interconnectivity. So we have many technologies and our groups have become closer together. We've been swapping technologies across the globe for a long time. The final way that we deal with this ever-growing amount of information, and I would say the most effective way, is by dividing up the labor. So dividing up the information. It's simply the case that I can't, with my limited brain, learn everything I need to survive. But if I'm in a large enough group, I can rely on at least, there's enough other people who can handle the other side of life for me. So I'm going to deal with each of these in turn. I'll return to the diversity one because I think it's the most interesting. So in the collective brain, we argue that there are kind of these three levers that I mentioned: sociality, transmission fidelity, and diversity or cultural variance that are driving the increase in cumulative culture. So sociality, there's lots of work here. So this is Klein and Boyd's paper on the relationship between population size and toolkit size, or they also have it in techno units. To be clear, the model that they're kind of connecting this to, the Henry 2004 model, is about sociality. So it's kind of effective cultural population size. Who do I have access to, which is a function of both population size and interconnectivity. And you can actually see relative to the regression line where the less connected and the more connected populations are. In my own work, within the innovation paper, we show, for example, that speaker size is well correlated, controlling for phylogenetic relatedness of these languages with the optimization on the information content. So you can calculate the amount of information that a word possesses using these large corpuses, such as what Google has. What does information mean? So in the paper, we use, surprise factor is an intuitive way to think about that. So you can look across the context, you find a word. So it is raining today. I should really bring if the next word is umbrella, that's very low information content because you could predict it on the basis of the other words. If the next word is, it is raining today, I should really bring my shotgun. Shotgun in that context has a very high information content. So what you can then do is you can look at the correlation between word length as uttered or whatever, and the information content. And you find that correlation is stronger when there are more speakers in the language. So it seems like they're shrinking words to be more efficient. WTF. And of course, you can look at this experimentally, this relationship between sociality and cultural complexity. So in various experiments, not only by myself, but Alex Masudi has a paper on this, Maxime Dere has a paper on this, where basically we adjust in across the different papers. This was also replicated, I think, very recently in that science replication, Nature and Behavior replication. We adjust, in our case, not the population size, we hold that constant, but the interconnectivity in two versions. One, we start people off in recreating this image in the GIMP, which is a difficult to use Photoshop equivalent. And then we start people off as naive experts and see how the rise goes and see if it's consistent with the theory. Kind of interesting, but I think more interesting is that we also start people off as experts in rock climbing knots, and then we look to see the decline and whether we find a different equilibrium emerge consistent with the relationship that the theory predicts, and we do find it. So across generations, when people have access to more models, we see this increase as predicted, and we see no change when they don't have access. I really like this paper in part because it's just obvious. You can actually see this very clearly. Here's the target image. Here's when they had access to only one model, and you can see it's a scatterbang, right? Like some people get it, but it just doesn't get transmitted along the lines. Whereas if you have access to even just a few models, once somebody gets it, it starts to reliably transmit, and we actually find that they're using multiple models to guide them, to the point where the worst person here is better than the best person here, actually. Okay. I think that's cool, but also not super surprising. What I think is much cooler, actually, is that we started people off as expert rock climbers. And then we look to see how they, again, transmitted information generation by generation. And what we find is a differential decline and then kind of a differential equilibrium that emerges. So larger, more interconnected populations have faster innovation and can sustain more. Now, this assumes no kind of technologies for storing that information, which of course increases the effective connectedness. I could read the classical works of Darwin, say The Descent of Man, and this is of course increasing our effective sociality. Books, radio, television, the internet, and so on. But it's also increasing the second lever, which is transmission fidelity, right? All of these allow us to transmit information more effectively per generation. The one that I think is most interesting is the diversity and division of labor factor, because it's kind of a two-sided thing. This is a preview. So in our model, I'm running out of time, so I'm going to do this really quickly. We find that the major mechanisms by which we innovate are incremental invention through partial models and trial and error. We hold in our heads all kinds of partial models of why we think we believe things, but honestly, I think that comes after the fact, right? Like, do you remember when fat made us fat? That made a lot of sense, right? Eat fat, get fat makes sense. Now it's like sugar makes us fat, and somehow that also makes sense, and well, I need to store that information or whatever. I would say that's not why you learn, and that's not why you believe it. Masks is another thing, perhaps to preserve PPE supplies. Masks are useless. I mean, you're breathing in your own stuff. It's terrible for you. No, everyone needs to wear a mask. So on. We all know the discoveries that were invented through serendipity, antibiotics, Velcro, the microwave, and so on. But the big driver that I think you can explicitly use in your own career to enhance your own creativity is recombination, and we see this simultaneous invention. Like if it really were the case that our individual genius was driving innovation, then we shouldn't be as afraid as we are of being scooped. And I think the reason is that we're all working the same milieu, and Newton and Leibniz both kind of arrive at the calculus, right? Darwin, like we're celebrating 150 years of the descent of man. Darwin, poor Wallace, right? He's a little bit late to the party and he gets forgotten. But in both their cases, you can see the recombination of, reading Malthus's Principles of Population, reading, the vestiges of the natural history of creation, visiting these island archipelagos where you can see evolution at work and kind of being breeders themselves, putting all these pieces together, right? This recombination. And so in the paper, we say, and I think innovation is no more driven by individual innovators, or they are no more important than, our thoughts are driven by a particular neuron. Of course, there was someone involved, and of course, there are differences between us, but that's not what drives it. Might take questions on that. The division of labor, I think, is the most interesting. Here's a stylized model of it. That we're working on. So imagine, I've got a maxed out brain. Can't birth anything bigger. If I have to learn everything, let's say 10 size brain, 10 items in a society, I can only reach skill level 1 on all of those. If I can dedicate myself to just half of those things because I know someone else handles the other half, now I can reach skill level 2. If I only focus on one of those things, I can reach skill level 10. And if I only focus on a partial thing, so I'm a doctor in New York, I focus on, a tiny part of the renal system, I can go very, very far in that. Whereas, in a smaller society or in a smaller village, you got to be a doctor that does many, many things, right? So even with our limited brains, even holding constant things like population size to some degree, you can go a lot further when you divide up the labor and you can coordinate well. And that coordination is the paradox of diversity. Intellectual arbitrage is an effective way to be creative, take something that's well established in one discipline, bring it to another. Lots of Nobel Prizes won in that way. But diversity is the fuel for the engine of innovation through recombination. But of course, it's by definition also divisive. If we don't speak the same language, good luck listening to this presentation, right? And so we need to find ways to kind of solve the coordination problem so we can take advantage of all of the goodness that diversity brings. Okay. I wanted to leave enough time to talk about intelligence, but I'll say it very, very briefly. So here are 10 facts about intelligence. The first, 10 facts about IQ as a measure of intelligence. So IQ is a good predictor of school, at least in weird societies. IQ is a good predictor of work performance, at least in weird societies. However, IQ differs in its predictive power and is the least predictive of performance on tasks that demand low cognitive skill. Jobs are classified based on information processing. IQ may be separable into crystallized and fluid intelligence. Crystallized intelligence refers to the knowledge that is drawn on to solve problems, and fluid intelligence refers to an ability to solve novel problems and to learn. However, I don't know if I say this here, but IQ, the largest gains are in fluid intelligence. IQ appears to be heritable, but heritability scores may be weaker for low socioeconomic status, at least in the US. It seems to be higher among kind of flatter societies like Europe and Australia. Educational interventions can improve IQ, including fluid intelligence, which is affected by things such as memory training, although there's lots of debate over how long those effects last. There is some causal evidence, newer causal evidence that I can talk to you about, but also, the classic like Brinch and Galloway, where an educational intervention, such as increasing the number of years of school, increases the overall population only among that group. IQ test scores have been dramatically increasing over time, and as I said, this is largest for fluid intelligence, but also largest for nations that have recently modernized. The largest gains have been measured on the supposedly culture-free Ravens test, a test that measures fluid intelligence. IQ differences have neural correlates. This shouldn't surprise you at all, right? Our major processing unit does everything. Our brains are as diverse as we are. It should be not surprising at all that anything that we can measure in behavior might also be found in the brain. You should be far more surprised if it's found, in the spleen or in the big toe or something. And populations and ethnicities differ on IQ test performance. In my view, that it's very difficult to reconcile all of these findings unless you realize that we focus a lot on the hardware, that giant brain of ours, but that is, kind of the limiting factor, and it has some room to move, as you saw in the birthing data. But a lot of it is driven by the software, and that software has been changing over time, right? Not only in our educational interventions, but elsewhere, as I'll show you in a minute. So when we think about heritability, I don't have time to go into this, unfortunately. When we think about heritability, it's of course well known that it's going to depend on the variation and the interaction between the genes and the environment. But But I think what's less well understood is the systematic way in which the cultural environment is evolving, and genes are changed. So the same genes, for example, let's say genes that protect you against malaria, might be positively associated with cognition in a place with malaria, and negatively associated if it's associated with sickle cell anemia, right? Other genes may do nothing. If you've got a genes that helps you acquire more calories from the environment or protect you against pathogens, they're useless in an environment where that doesn't happen, right? Take a look. There's a model of how you can look at the systematic changes within the cultural environment and how that would affect your heritability score, as well as how things like tightness and looseness might affect the trajectory that you find as new innovations are created and as they diffuse. So you get this kind of shifting, although there's this kind of cumulative culture, as a new innovation, let's say a new educational invention. Elon Musk's Ad Astra school or something like that. Let's say it works. Initially, only those in Silicon Valley who manage to get into the school can take advantage of it. Eventually diffuses to the whole population. And once again, genes might be predictive. And of course, our society is becoming more complex, right? Consider Adam West's Batman versus The Dark Knight, the Avengers Endgame, or the Avengers in general, I Love Lucy versus Rick and Morty, Christopher Reeve Superman versus the Avengers, and so on. So it's not just that our schooling has gotten more complex, our very ways of thinking, every job has gotten more complex and more complicated. Our media has gotten complicated. It used to be like a simple storyline. Now I got to track all these characters doing all these crazy things. There's just a higher level that's expected. I want to end in the last 2 minutes that I have, so that there's 15 minutes for questions. I think that's right. The next 150 years. I don't normally think in century and a half timelines, but I think these are the kind of things that we're laying the foundations for the future of the descent of man. So the first, I think, is completing the Darwinian revolution. This is also kind of some recent work of mine. So moving toward a more general theory of human behavior. So, once upon a time, the physical world was chaotic. It was a world of capricious gods. And then along come people like Newton and Maxwell. And somehow the world is a little bit less chaotic. And, eventually we can do quite a lot of prediction. Once upon a time, Newton himself is trying to turn lead into gold. And engage in alchemy, but the chemical world seems chaotic. We can make gunpowder. We don't quite understand how it works, but it's unclear whether lead into gold is a real thing or not. You mix something, you mix a liquid with a solid, and suddenly you're getting a gas. And along comes Mendeleev and the periodic table and collision theory and an understanding of atoms and elements, and suddenly the world is a little bit less chaotic. The biological world felt pretty chaotic. Why do some animals have the horns and the wings, and it's just crazy? And along comes Darwin and Wallace, let's say, and others, and suddenly the biological world is a little less chaotic. We still can't predict ecology super well, but at least we understand the rules by which they operate. Today, the human and social sciences feel chaotic. Why are some countries successfully dealing with a pandemic? Others are not. Why are some political systems seem to be working and others don't? What is driving innovation? Why is Silicon Valley working and other places don't? But I think we're at the cusp of understanding at least the rules by which these systems operate. There are, however, I think some things that hold us back. One is, I guess, training in this stuff, cultural evolution going mainstream. The second is that I think sometimes what it takes for science to move forward is to let go of assumptions that hold us back. When we let go of the assumption of a solid Earth with the sun tracing the sky, we get a better model of the solar system, right? I think one of the assumptions that really holds us back is some of the assumptions around human intelligence, the focus on the brain, the focus on the neuroscience, and the focus on the idea that there's some deep human thing that you can measure. And that is what has led to our success all around the world. And I think a shift to to understand the relationship between the hardware and the software gets us a lot further. The second thing is, I think, an underappreciated finding in psychology that holds us back is the illusion of explanatory depth. And that is kind of like the fat, making us fat and the sugar making us fat and the masks. We walk around with the belief that we understand the world in far more detail than we do. In Frank Keel's work and Rosenblatt's work, they ask people things like, how does a helicopter work? And if I hadn't primed you, you'd say, I have some sense for how it works. But when you ask people questions like, well, how does it how does it go up and down? You're like, I can imagine rotors doing that. Okay, well, how does it turn? How does it go forward and backward? And suddenly you're like, well, Or another example, another couple of examples, a flushing toilet, centuries-old technology, hopefully interact with every day. Can you make one? Do you know how it works? How it flushes everything away? You might have some sense that you do until you think for a second, like, how does it flush everything away? And why does the water always return to the same point? So you're like, pipes and shit. I don't know. Or antibiotics. Everybody knows to avoid superbugs, got to finish your course of antibiotics, right? You got it, right? I mean, that makes causal sense. Until you stop for a moment, you're like, but wait, like, surely you don't kill 100% of bacteria. And that just increases the selection pressure. So then doesn't it mean that the most antibacterial resistant germs are the ones that are going to survive, the bacteria? Doesn't it mean you're actually increasing the selection pressure? Well, actually, it is more complicated. There is an optimal point. We just don't know where it is. And so we give people enough to get them close to it. The point is that the world is more complicated than it seems, more complicated than our psychology would even allow us to believe. And I think understanding that helps us let go of that assumption. I think there's also a shift in emphasis. Dual inheritance theory, the extended evolutionary synthesis, cultural evolution was born out of human origins. And a lot of the focus is still there. But I think what's interesting is, how does it work today? What does it mean for human futures? Integration with the other sciences. The second kind of next 150 years, I think, is beyond weird psychology. This has been done to death, but wider, deeper, longer term historical data across sections of society, across the lifespan, is the only way to kind of test these theories that we're building. And the third is what I guess is cultural evolutionary public policy. If your theory and your data doesn't work in the real world, it doesn't work at all, right? You want to go beyond, anthropology of non-weird outsiders trying to understand how a society works to collaborating with groups. Sorry, I'm still talking about the beyond weird psychology, collaborating with individuals from those. I forget ETIC versus EMIC or whatever, but in collaboration, we can begin to measure societies in a richer way. And we can also begin to test things across the world through cultural evolutionary public policy. And that requires, of course, integration across the human and social sciences and using application through policy. I shall leave it there. I want to make sure there's enough time for questions. All right.
Well, thank you, Michael. This was really great. Thanks a lot.
Shall I stop my screen share, Sergey?
Yeah, maybe, yeah, so people can see you better.
Okay.
Yeah, okay, so we have a bunch of questions here. First one is about bears, who are carnivores with very large brains as compared to wolves and dogs, who are very social, and wolves cooperating in hunting and such. How do you explain such large brains in a rather solitary species outside mother-offspring bonds?
So I must admit, I don't know enough about, or is it Ursula, like bears? I just don't know enough about them. One thing I will say is you cannot compare, across such different taxa. You have to compare, within, let's say, different bears, different kinds of bears. The second thing, of course, is that it depends on the ecology. So one of the predictions is that a richer ecology results in a larger brain and a larger body, simply because there's more energy, there's more stuff that I can exploit, right? Whereas in a poor environment, I can't. So I would say that I would suspect, I would be shocked if the more social dogs did not have a larger brain because they're more social. Whereas if bears, I don't know enough about them, but if they were asocial, then it might predict the opposite. So you might say that very asocial bears, or no relationship at all, and it's driven by other features because the predictions for the asocial are very different.
Thank you.
We'll know a little bit more, at least, about the octopuses within 3 years. So I'll get back to you.
Just I have a comment. I see some people put their questions in chat. Please do it for Q&As because it's more difficult to keep track of that. Okay, there are two questions on self-domestication. How does your work relate to self-domestication, hypothesis and human evolution? A lot of the features you mentioned are aligned with domestication syndrome, extended juvenile period, larger brain, social networks, and then there is another one I'm trying to relate this work. With Christopher Bohm reverse dominance hypothesis, a more recent framing in terms of self-domestication in humans.
Okay.
The origin and spread of capacity for symbolic thought. Yeah.
So there's kind of two questions there. The first is about self-domestication, which I'm completely on board with. I think of this kind of this autocatalytic takeoff is like we are evolving to our cultural environment very much so, right? Like the skill set that I have is kind of useless outside of a highly cultural university ivy covered ivory tower environment. And so there is this kind of self-domestication that's going on. How does it link? So the Christopher Boehm reverse dominance hierarchy stuff is a little bit different. So we do have some new work trying to understand the egalitarianism that we see in some hunter-gatherer groups and not others. I don't think the way to think about that is like this was an ancestral human condition or something like that. In our empirical and theoretical project, we suspect that it's an adaptation to property rights and the competition in the environment. But I need another talk to get into that. Yeah, thanks. I think there might be a working paper related to it.
Thank you. There's a question from chat. Have you considered how cooperative breeding could also help to explain long juvenile period? Juveniles can care for and be models for very younger relatives.
Yeah, I haven't seen that formalized, but I think in general cooperative breeding probably supports a longer juvenile period. Yeah, you can have maybe more kids, but also just offload some of the care to the older kids. The advantage I think of the older kids looking after the younger kids that is lost sometimes in our society is the age gradient, right? It's easier for a 3-year-old to learn from a 5-year-old than it is like in our society. We literally have to train specialist teachers. I don't have to train my 5-year-old to teach my 3-year-old because it's just intuitive. They're close in age, right? And so that age gradient is lost in our education system, even if we've got other efficiencies. I just haven't seen enough work on the exact relationship with cooperative breeding, so I can't say too much more about that.
Thank you. And there is also another question from the chat. Hi, Michael, I like your work and I'm enjoying your presentation. A question, social and individual learning involves the acquisition of existing knowledge. Do you also take into account the generation of new knowledge? And as a simple example, for social and individual learning, you can learn that the world contains snow and men, but it takes creativity to realize that it could also contain snowmen.
Yes. So in fact, so this is the kind of famous Rogers paradox, it's like we're all social learners. Where's the new stuff coming from? So that's those mechanisms. So I think those are some of the sources of learning. So copying errors, that's the kind of serendipity. You've got the incremental, we do have some amount of causal knowledge, right? You are an expert. You're using that, let's say, 10-sized brain on something, and you do have some amount of knowledge of that one thing. And I think you can make small advances, even if a lot of them, you have a higher probability of making an advance that's useful than someone who's not, right? We are not relying on economists to develop a vaccine. We're relying on people who are experts in that area. And of course, recombination, as you pointed out, the snow and the snowman, that's probably a big driver. I really like that one because I think that honestly, you can do this deliberately. We should have like business training programs on how to do this explicitly, solving that paradox of diversity, figuring out how to kind of consciously recombine things. Yeah.
Thank you. Next question. Very interesting talk. Thanks. You mentioned that it would have been necessary to unlock resources, I guess, to produce big brain. One crucial mechanism to unlock resources for juveniles is paternal provisioning, in particular of meat. In a recent paper, my co-authors and I proposed a theory that allows us to predict when it would evolve. And the data seem to suggest that it was probably happening about 2 to 1.5 million years ago. Do you have any comments on this?
That sounds fascinating. So please do send it to me. Just send me that paper. Paternal provisioning is probably a big part of it. I think that is why we see this regular pattern of kind of controlled female sexuality and controlled paternal resources.
Thank you. An extended juvenile period could also evolve if reproductive opportunities are limited and fiercely competed over, as observed in birds. In the same species, some intelligence could be necessary for gaining these opportunities. Is this a possibility, I guess?
I don't quite understand the question. Maybe send an email about it. Unless you want to clarify the question.
Okay, all this will be here on the.
Okay.
I guess there is a comment from Rob Barton where, in addition, recent studies with bigger sample sizes question the link between brain size and group size.
Yeah. I mean, I'm not. I guess. Yeah. I guess maybe Rob and I can talk about that in another time. Otherwise, I think we'll spend the rest of the time on that. But it's good to be aware of that. Let's amplify that there is a debate around even the fundamental relationship between brain size and group size. And of course, we wouldn't necessarily, like, for example, in cetaceans, we don't see it between brain size and group size. We see it as this kind of sociality. It would be nice to think about the cultural brain hypothesis specific predictions against those larger data sets, and I'm happy to chat about it.
Okay. You seem to suggest that all information is useful. The internet suggests that some information that spreads is actually harmful, which means that we need also our brain to assess potential information.
Right.
In any equivalence in cetaceans, in dolphins, and.
Oh, I see. So I don't know how much fake news is going around dolphins. I don't think there's a lot of it. Maybe there's the occasional, I saw some food there. Oh, look, it swam away. Turns out it was wrong. But I don't think all information is useful. I think a lot of it is filtering. I mean, so one of the reasons language, people like to point to big brains and language and so on as the ultimate explainer, is that I can lie. Right? I can lie with language. And so you should be watching out for that. But that's an arms race. It's an arms race on my sincerity and the cues that you might use. And it's an arms race that's going on right now. So I think the problem with fake news is going to be solved in the next generation because they're just going to be savvier. So you were not, to kind of like tip into kind of Celia Hayes's kind of points, you were not born with a sense that like nice typeface equals New York Times equals trustworthy. You learned that. You learned some of the cues for learning. Right. And so, in the same way that like you get, there's this memes about forwards from grandma, like grandma is, it's a bit sexist, but forwards from elderly, they're just gullible. They were not equipped to deal with like this kind of world. Their cues are off. But I think the kids of the future will have the right cues. They will be able to distinguish what's clearly false and not. But maybe that's wishful thinking. But certainly I think the framework is useful for thinking about fake news.
Thank you. And there is kind of related question. Any thoughts on whether and how the internet will affect the collective brain, positively or negatively?
Yeah, so I think on the whole, positively. So everybody complains about like the fights on Twitter and and all this, but that's a good thing. If you're having battles on Twitter, it means you're being exposed to things you don't like, that you disagree with. That's a good thing. Twitter, to me, this is not the fourth industrial revolution. This is the coffee houses. This is the Enlightenment. This is the precursor. This is the sharing of knowledge that leads to the next industrial revolution, which would have to be kind of an energy revolution. So I think it's a net positive, even if there are some costs. There are some other costs that I'm writing a book at the moment. I'm gonna put that one out there, and I deal with this a little bit in there. And in there, I talk about the fact that you can get smaller minority groups that didn't have collective, like you can connect with people who are not in a sufficient critical mass otherwise, and so this destabilizes the system somewhat, especially anyway. Mm-hmm. Bigger topic. Yeah.
There is a definitional question, I guess. Is there a difference between social learning and cultural learning?
Rose by any other name, but I think the normal way that it's spoken about is kind of, social learning can be a bit much broader category, which might include things like I'm near the animal that's engaging in the behavior. Because I'm near it, I'm also learning that. Whereas cultural learning is about this, this culturally transmitted knowledge. But honestly, like Rose by any other name.
Okay, thanks. Could you talk more about whales and dolphins? Have they entered the cumulative culture, sociality, brain size, positive feedback loop? And if so, what factors limit how far they can go?
Yeah, I don't think that they have. I think that they are quite, they're quite sophisticated, but they haven't got that autocatalytic takeoff. I mean, there are a few things, for a few reasons that I think it's difficult for them. So one is hands. Being able to manipulate things really increases the affordances that we have. And that's why I think like bipedalism as a pre-adaptation may have been helpful. And the second thing is it's really hard to light a fire underwater. And without a fire, we can shorten our guts and we can trade off that tissue for bigger brains because we're cooking our food. Now that, of course, we don't have adaptations for how to light it. We don't have genetic adaptations for how to light a fire or even how to cook. We are born into an environment assuming language and assuming cooked food and assuming all those things we need to survive. But that allows us to pay for these big brains because we can unlock more calories and nutrients, which dolphins don't and orca don't have access to.
Mm-hmm. Thanks. Yeah, let me ask you one more question from the audience, and then I'll ask our panelists, speakers in this series, if they have any questions.
Sure.
Great talk. Thank you. Chicken egg question. A lot of species haven't encephalized, obviously, with these feedback loops between increasing brain sizes due to mutations and increasing group size complexity. How does this looping process begin in the first place and continue to feed itself?
Yeah, no, great question. So the first thing to note is that, there's no kind of endpoint, right? Even in our models, all of those blue and red points that you saw, those are like, equilibrium species, right? So there are humans and there's also chimps, and we haven't fully pushed them out yet. We still have bacteria around, right? There are other species there. For the human case, I do think there are these kind of starting conditions if you're talking about the human autocatalytic takeoff, and I outlined some of them. So one is we find that if you don't have that initial knowledge to exploit, it can be hard to get the takeoff going. So I really think that kind of rapidly changing environment, I'd love to hear what Pete has to say about this, but that rapidly changing environment followed by the moderate change may have been crucial. The second thing is things like generation length, right? Like the moderately changing environment has to match up with generation length in some way, that autocorrelation. Having things like hands were probably helpful. Cheapening the tools, providing the basis for ratcheting up. In related things, when it comes to say cooperation, it can be hard to kind of skip steps. So I think there may have been kind of a gradient that all of the pieces were right there. I think Rob has this, I think he has this book. I can't remember what it was. One of his papers, he says, you need the general patterns, but then you need something special. And so there's something special is, I think, some of those initial starting conditions, and we can only speculate. There's not enough data.
Thanks. Pete and Lou, I wonder if you have any questions. Pete?
Yeah, Michael, I'm under the impression that we don't really have any kind of empirical sign of autocatalytic increases in brain size during the Pleistocene. The brain size increase looks pretty linear to me. And now in the Holocene, after the brain size has already evolved, and we do have what looks like it's an autocatalytic innovation process that the exploding population is it's a hyper-exponential process. Actually, it looks like very slow change in the early Holocene and a very rapid ramp up in the last few centuries. So that looks autocatalytic, but the Pleistocene brain size increase in humans doesn't look very autocatalytic to me.
Yeah. I agree with it. Obviously, I agree with the data, Pete. But so, I guess the only way for this hypothesis to be true is so you're talking, so once you max out on brain size, those genetic changes, then, you've got there's the autocatalytic on the cultural stuff, but there's a lot of cultural stuff that was probably possibly being transmitted that is lost. So if they had, for example, wooden tools, what evidence would you expect to see of that, right? Or even bone tools, like, how much evidence are you expecting to see? We know that we had fire very early on, and we know that chimps don't have fire, and we know that it's hard to get fire, it's hard to make a fire, it's hard to get, there was stuff being transmitted. And so, I think it's entirely plausible that lost temporary cultural stuff was driving up the brain size, or simply, transmitting knowledge through language was driving up the brain size in a linear fashion. And then you kind of get this takeoff on the stuff that stick around that you can measure much more easily. So there's maybe like a bias in the data that's available to us.
Let me actually ask a kind of continuation or related question to what Pete just asked. He and Rob have been pushing that idea that it was increasingly unstable environment that made cultural evolution powerful and possible. But I don't think you ever mentioned the role of environment in your models.
No, so yeah, I mean, sorry, who asked the question?
Pete Richardson and Rob Boyd.
I see. Yeah. No, so I mean, implicit in the cultural brain hypothesis is the role of environmental variation. It's not explicitly modeled, but I mean, I'm assuming that in some of what's going on here. So I think the rapidly changing environment and the kind of the moderately changing environment, the zones of genes as an adaptation or individual learning as an adaptation versus cultural learning as an adaptation. And once you're in that zone of the cultural learning, building on what came before, now we're in the realm of the cultural brain hypothesis.
Mm-hmm. Okay, thank you. Let me go back to Q&As. So you've been kind of touching on some quite controversial topics, so I guess you'll be able to handle the next question. How do you feel the impact of improved medical technologies, for example, increase in success in childbirth, and has affected the natural selection progress of smart ancestors and the increase in social and the increase of social disabilities such as autism? Has cooperating breeding changed the trajectory of natural selection?
Yeah, so this flavor of question, I think, breaks the world up into like natural stuff somehow and then cultural stuff. But for our species, those two things are always hand in hand. So we can talk about specific things. So, for example, I do think it is the case that cesareans relax the selection pressure on those bigger brains. So there are a lot of big brain humans that would have had a very difficult time with childbirth that are now being born. Now, there's cost to that, right? So the microbiome transfer that normally takes place as the baby comes down the birth canal is gone. Respiratory problems because, there's not enough of a kind of squeezing on the lungs and so on. There are kind of versions of like natural cesareans where they use the mother's own organs to kind of push down on the baby and squeeze some of that out, right? And they do like seeding. So you can do like a vaginal seeding to like seed the microbiome transfer early on. So there are costs that come with it, but it's relaxing the selection pressure. Yeah, of course. I mean, it's going to allow for more diversity, more variation, and maybe also with more assortment, you might see more of these, so a little bit of, so if you have schizophrenia in your family or if you have autism in your family, that can be associated with math or creativity or whatever, but you might have kind of more extremes out there. You can tolerate a lot of diversity. And that diversity can be a fuel for innovation because you never know when it's going to be needed. But how much of that you can handle, I think, it gets into how much resources are available and scarcity and all that stuff.
We have a lot of more questions, but I think we need to let you go, Michael. Michael has been teaching since early morning today.
I have. My eyes are red. It's because of it. Yeah.
Yeah, and it's already evening in London. So I think we should thank you.
Oh, thank you. Thank you for inviting me.
All questions will be available on the webpage, and I suggest people just contact Michael directly. Thank you very much, Michael. Again, thank you very much to everybody who's been here, and hope to see you next week when Lou Barrett will be talking.
Brilliant. Thank you for having me. Thank you for the amazing questions. Have a good evening. Bye.